In the previous lecture, we had seen flow through confined aquifers in which there is an impervious layer at the bottom and also bounded by an impervious layer at the top. So what it means is that the thickness of the aquifer remains constant, or in other words, it does not depend on the head. The piezometric head will vary. If we take water out of the aquifer, then it will typically decrease towards the well, but the thickness of the aquifer remains constant and therefore the flow area remains constant. Compared to this, the unconfined aquifer doesn't have an impervious confining layer at the top. So if we look at an unconfined aquifer, there is a layer at the bottom which is impervious, and then the ground level. The unconfined aquifer, the water table will, the groundwater table would be open, and therefore the pressure on the top of this will be 0 or atmospheric. So once we start pumping an unconfined aquifer with some discharge Q, the water table will go down and it will keep on going down as we keep on pumping till it reaches some steady state conditions. And what we can notice from here is that the area of flow, earlier when we didn't have any pumping, the area of flow is the whole thickness of the aquifer, but as the cone of depression increases, the area of flow becomes smaller. So the height h will represent the area of flow. Therefore, the governing equations will be slightly different compared to the case of the confined aquifer. So let's look at the governing equation for an unconfined aquifer. Typically, let's say that this is the groundwater table, which is having certain slope. That slope depends on what is the pumping rate. Higher the pumping rate, more will be the slope. This is the height h, and suppose we take an element which is delta x in the x direction and delta y in the y direction. There are some assumptions which we have to make in order to be able to solve this. First of all, these assumptions were suggested by Dupuis, and therefore they are called Dupuis assumptions. Which enable us to solve unconfined aquifer flow problems. The assumptions are two. The first assumption is that the curvature of streamlines is small. So if you look at the streamline pattern in the unconfined aquifer case, they may look like this, but the first assumption says that the streamline curvature can be taken small and therefore the flow will essentially be horizontal. The second assumption is that the hydraulic gradient can be taken as the slope of the free surface. And the hydraulic gradient will remain constant over height, so it will not be a function of z, where z is the vertical coordinate. So if we take an element like this element, the hydraulic gradient for this whole depth would be given by the slope of the water table, and it will not change with depth. So using these two assumptions, we can now write the mass balance for this element. So we are drawing that element of the unconfined aquifer here, which has certain velocity here, qx, the Darcy velocity which is coming in, and therefore we can write the mass which is coming in through this face. So let's first compare the x direction inflow and outflow. The axes of course are x, y and z. So inflow in the x direction would occur through this face, the Darcy velocity is qx multiplied by the area, which will be h delta y. This gives us the amount of flow in terms of volume, and since we are interested in the mass, we will multiply it with the mass density rho. So rho of qx h delta y will be the mass of flow coming in from the left hand face. There is some mass which is going out in the x direction from the right hand face. So we can write that outflow as, using the same methodology as we used before, plus change of this quantity multiplied by the length delta x. So if we consider the x direction flow from both faces, the net inflow of mass would be equal to minus if we look at this equation, qx can be obtained from the Darcy's law. Rho we can assume to be constant. Delta y of course is the element thickness, which is constant. So we can write this equation as rho delta x delta y. Qx, let me write it here, can be written as minus k using Darcy's law. We will again assume that the aquifer is homogeneous and isotropic, so k does not change with location as well as direction, and therefore k can also be taken out of the differential. So we can take k out of this, and what we will be left with is del by del x of h partial h with x. We can further simplify this equation by noting that the h del h by del x term can be written as half partial of h square with respect to x. So if we use this we can write the net inflow rho so we get the second derivative of h square. So if we compare this with the unconfined aquifer and confined aquifer, if we compare, we will see that in confined aquifer we had here the second derivative of h, but here we are getting second derivative of h square. Now this was in x direction. We can write similar expression for flow in the y direction. The mass inflow in the y direction would be in the z direction. Due to the Dupuit's assumption, there is no flow component, velocity component in the z direction. Therefore, the only flow in the z direction for this element would occur if there is some infiltration from the ground surface. This is typically known as recharge. For example, there may be a rainfall event which will cause some recharge, or there may be a river which might be contributing to the groundwater. So this recharge is generally expressed in terms of R, rate of recharge, which tells us about the volume per unit area per unit time. So R has units of, for example, rainfall intensity. So it will be centimeter per hour or millimeter per hour or centimeters per second, depending on what units we are using. So this, if there is rainfall, then typically it will be the intensity. It will depend on the intensity of rain I, and depending on how much infiltration we are getting, that R will be equal to that infiltration. So let's say that there is some recharge rate R, and the mass which will come in because of this recharge from the top. Again, bottom we are assuming impervious, so there is no flow from the bottom, and therefore the recharge which will occur would be per unit area. We have recharge rate of R, so multiplied by the area of the element, which is delta x delta y, and multiplying by the mass density will give us the mass inflow in the z direction. So after knowing these net inflow of mass into the element, what we are left with is how to find out the change of mass within the element, and for that we will be using the specific yield. So how to find out the change of mass within this element? A specific yield, as we have seen already, a specific yield is the amount of water released from storage for a unit drop of head from a prism of unit base area. So here, since the base area is delta x delta y, we will have to multiply the specific yield with delta x delta y. So if we write now the total mass inflow combining all the x, y and z direction, so in the x direction this is the flow, in the y direction. This is the flow. And then, as we have seen here, in the z direction, rho r. This should be equal to the change of storage within the control volume which we are considering. So, mass released, or we can write mass change, would be equal to the specific yield SY area, and then the change of head, because specific yield is defined as the change per unit surface per unit area of cross section for a unit change in head. So we have to multiply with the area and multiply with the change in head. So this will give us the rate of change of mass within the control volume, and continuity equation says that these two should be equal. So we can write the equation as there is volume, it has to be multiplied by the mass density. So we can combine these and write it as K by 2 rho del x del y. I will write here and then cancel it out. So these will cancel out, and the final equation which we get plus 2r over k would be equal to 2 sy over k So this is the equation which governs the change of head with time and space. Change with time is here, and change with space will be given by these two terms when it is subjected to some recharge R. Most cases which we will deal with, we can assume that the recharge is 0. In confined aquifers, of course, since there is an impervious layer at the top, unless the layer is slightly pervious, there will be no recharge. So therefore, typically we have not considered recharge for a confined aquifer. But sometimes confined aquifers, the overlying layer may not be completely impermeable. It may be an aquitard which will allow some leakage into the confined aquifer. In that case, in confined aquifers also, we should consider the recharge. So this equation needs to be solved with different boundary conditions and initial conditions to get the variation of H in an unconfined aquifer. So we will take some simple cases. For example, if we take steady state flow, then this term will be 0. Steady state, this term will be equal to 0. Similarly, if we say that there is no recharge, then this term will drop off. So in the absence of recharge and for steady state conditions, we will get an equation which is similar to the equation which we had for confined flow. There we had Laplacian of H equal to 0. So the only difference is that instead of H, now we have Laplacian of H square as 0, which we can solve to obtain the value of H at different locations. So let's take an example in which, similar to the confined aquifer case which we had considered, ground level, and let's say there are two water bodies which have elevations of H1 and let's say that there is a length L, x is 0 here, and then at certain x we want the location of the groundwater table. So in the confined aquifer case, we have seen that the water table was a straight line because h was linear, but here it will not be a straight line, so we should find out whether it is like this, or it is like this, or like this. So this is what we are interested in, finding out what is the value of h at any x. And to solve this problem, we can assume that there is steady state condition, one-dimensional flow. So if we assume one-dimensional flow, then the equation becomes straightforward. What we are assuming is no recharge and steady state one-dimensional flow. So if we make these assumptions, the governing equation will be reduced to, this term will be 0, r is 0, this term will be 0, steady state, and this term will be 0 because the flow is one-dimensional. So we are left with this very simple equation which we can solve and obtain that h square will be linear. Now these constants can be obtained from the boundary condition, and in this case the boundary conditions are x equal to 0, h is equal to h1, and x equal to L, h equal to h2. So you can see that C naught will be equal to h1 square, and C1 will be equal to h1 square minus h2 square over L. So using these two values of C0 and C1, we can obtain the value of h, and since h square is linear, the actual level, the actual groundwater table will not be linear, and we can see the discharge Q at any location x. Q can be given as K I A, where K is the conductivity, hydraulic gradient, and the area of flow. I in this case is del h by del x, and this negative sign will be there because we are saying that the flow will be in the direction of decreasing head, and the area of flow at any location where the height is h, if we consider unit width perpendicular to this, so the width perpendicular to the plane of the paper, let's say delta y is equal to 1. So per unit width, the discharge can be given as minus k del h by del x into h, and this can also be written as we have done earlier for deriving the equation. We had seen that del h by del x, h del h by del x could be written as half partial of h square with respect to x. So using that, we can write this in terms of partial of h square with respect to x square, and we know that from this equation this is partial of h square with respect to x. So we know that partial of h square with respect to x is equal to c1, and therefore it will be simply q will be given by minus k by 2 c1. Now if there is some recharge, so here we had assumed that recharge is equal to 0. If there is some recharge, then we will have to add the recharge term and from this equation this 2r by k term will also come. So the equation derivation is similar, but now we have to account for the recharge, and in this case we will see that the groundwater table may rise above the level H1 because there is recharge coming in here at the rate of R. So because of this recharge, groundwater table may rise, and we can find out the equation of this line by solving this equation with the boundary condition which are same, x equal to 0, so using these two boundary conditions we can obtain the value of h. If there is no recharge, then of course minus k by 2 c1, and c1 we have already obtained from here as h1 square minus h2 square over L. So without recharge Q will be k by 2 into C1 k by 2 into h1 square minus h2 square over L, and there is a negative sign here. C1 is minus h1 square minus h2 square over L, and then this is the value of Q. With recharge we have to add this 2r by k term, and then we can solve the equation in a similar form in which h square will be C naught plus C1x minus r by k x square. Now this comes again by solving the differential equation which we had written here. And applying the boundary conditions, we can obtain the value of C naught. C naught will again be equal to h1 square, but C1 in this case will be different from the C1 which we have derived earlier when R was 0. In this case the C1 turns out to be minus h1 square minus h2 square using the boundary conditions x equal to 0, h equal to h1, x equal to L. So Q again will be given by the same equation minus k by 2 C1, but now C1 will be a function of R. So we have k, then we have h1 square while in this case it was only h1 square minus h2 square over L. Here it would be h1 square minus h2 square minus r over k L square over 2L. So if we draw the profile of the water surface, this is the ground level, there may be a water body here. In practice, this may denote a river or a canal. So if we have two rivers or two canals which are running parallel in the unconfined aquifer, the water level in absence of recharge would look like this by plotting the equation, and when we have recharge, the water level would look like this. In order to find out this equation, and just by looking at this we can see that there is a point here where H will be maximum. And if you look at this, whatever flow is occurring on this side will move towards the water body on the left, and similarly the groundwater flow from this side will move towards the water body on the right. So this portion can be called a groundwater divide. So because of the presence of the gradient in this direction here and the gradient in this direction here, the groundwater will flow towards one side, so this side, and towards this side. So this line can be thought of as dividing the groundwater such that one part flows into one water body and the other in the other water body. We can find out the location of this point also. For example, the Q value is known to us. Now this may not happen in all cases. It depends on what is the rate of recharge. If the rate of recharge is small, it may not happen. It may be below H1 all the time. So it will depend on the rate of recharge, and we can find out what is the critical rate of recharge at which the groundwater divide will occur. So for that we need to write the equation for Q as we had done here. And you can see that for at the groundwater divide, Q will be equal to 0, because before that Q will be in the negative direction, after that Q will be in the positive direction, and just at the groundwater divide Q will be equal to 0, and this will give us a relation between the recharge rate and the location x. For example, when there is no recharge, we know that Q is k by 2 h1 square minus h2 square over L, which is not dependent on x. Now if we have the recharge, then Q will depend on x also. So there is a constant term Q, and there is which is the same as without recharge. So if you look at this term, this gives us the constant term, and the second term will be with recharge, so R by K L square, and this Q will be dependent on X also, 2R by Kx. So if we look at this point, this line, the Q term has to be 0 on this line, and therefore what we get is 2R by K let's call this point x naught. So 2R by K x naught will be the dependent space dependent or spatially variable value of Q. This changes with space because of the recharge. So there is some recharge coming in from the top, and there is some flow, let's say, coming in from this water body or going into this water body. If we take any section here, the amount of flow which is coming in because of recharge is R into whatever delta x we have considered. So if you take Q at any section here and Q at a section here, the difference between these two Q's will be the amount of recharge coming into this from the top, which is R delta x. So when we look at this situation where we have some value of x naught, minus 2R by K x naught should be equal to minus C1. So x naught will be equal to K by 2R C1, and C1 in this case we have already obtained is minus H1 square minus H2 square minus R by KL square over L. So we can write x naught as L by 2 So this gives us the position of the groundwater divide, and for groundwater divide to occur, x naught must be positive, and therefore we can find out what is the recharge rate, critical recharge rate, which will cause a positive x naught. So for x naught to be positive, we can find out the critical recharge rate. R should be greater than K H1 square minus H2 square over L. So what we have seen here is that if recharge is greater than this value, H1, H2, L and K, they are the properties of the medium and the boundary conditions. If recharge rate is greater than this, then we will have a groundwater divide, otherwise we will not have a groundwater divide. So for unconfined aquifer, flow between two water bodies, one-dimensional steady state condition, we have derived some expressions, for example this H square. Using this H square, we have obtained as a constant value C1 and a time space dependent value 2R by K x. So when we find out the Q as minus K by 2, it will have a constant value and a time dependent value, which is Rx. This we have seen is the contribution of the recharge up to certain distance x. So for example, if we have this recharge occurring r here, and there is some q here, I will show it in the positive direction, but it may be towards the water body, then at any other x, what it says is that q here would be q at 0 plus Rx, and this term Rx therefore represents the contribution from the recharge to the discharge. Then we have seen that there will be some point x naught at which the water table will reach a maximum value, and therefore it can be taken as the groundwater divide. The location of this point x naught can be obtained by putting q equal to 0, and since q is equal to minus kc1 by 2 plus Rx, x naught will be given by k by 2 Rc1, which can be obtained as this. For a groundwater divide to occur, x naught should be positive, and therefore R has to be greater than k h1 square minus h2 square over L. Typically L will be large and h1 square minus h2 square and k, all of them will be small. So if R is larger than this, means if L is very large, then this value will be very small, and a very small value of R will be sufficient to cause the water divide. So this q, of course, you can find out q at any location. In the portion before x0, q will come out to be negative, and in the portion after x0, q will come out to be positive. That means it is going in this direction. Before x0, it is going in this direction. So this is a one-dimensional flow situation which may not occur in practice very often. What is the most common situation occurring in practice is flow towards a well. So we will next look at this case of an aquifer, unconfined aquifer, being pumped at a rate of q, and we will try to find out what is the steady state drawdown cone. So this cone of depression at any distance, now we will be using r because now we want to use radial coordinates. At any distance r, what is the height of water table h, or in other words we can also think of in terms of drawdown s. Given that initial thickness of the aquifer is capital H, now the equation will remain the same. We have let's assume that there is no recharge, so R is equal to 0, so no recharge. And then we also assume that there is some water body supplying it enough water so that it has reached a steady state and there is no further depression of the cone. So in that case, we have our governing equation as Laplacian of h square equal to 0, because there is no recharge, steady state conditions. And as we have seen earlier, for radial coordinate system, we can write the Laplacian of h square as this. We need two boundary conditions to solve this. Generally, there will be two drawdown values available to us, or we must have two drawdown values available to us. Let's say at R1, H1 and R2, H2. Now these R1 and H1 and R2 and H2 can be taken anywhere, but a commonly used method is take R1 as the radius of the well. So if the well radius on a very large scale, if I show the well radius, this is the ground level, initial water table at a depth of h, and then a steady state drawdown cone may look like this. From the center of the well, we can write RW at the radius of well, and we have already defined a radius of influence, that is the distance beyond which there is no drawdown, and typically we denote it by capital R, although we have used this R for recharge rate also, but there should not be any confusion. So this R is the radius of influence. So by measuring the drawdown in the well, SW, or we can say the height of water in the well is HW. So the equation which we are solving is the Laplacian, subject to two boundary conditions, R equal to RW, H equal to HW, and R equal to R, H equal to capital H. The solution of this equation can be obtained as we have done for confined flow case. Where C1 is some constant, and therefore it will give us identical to confined aquifer. The only difference is that instead of H, we now have H square. This tells us how the head varies in the aquifer, and we can also find, using the boundary conditions, what are the values of C1 and C2. C1 is the one which is really important for us, so we can write C1 as H2 square. For any R1 and R2, we can write H2 square minus H1 square, or if we take these RW and R values, then it will simply be H2 can be taken as capital H, so if we take RW and R values, then this will be equivalent to and R by RW. The discharge at any point Q can be written as 2 pi R K H, and I am not putting negative sign here because the discharge is in the negative R direction, therefore this negative sign I am not putting. Now this H del H by del R, this 2 pi R is the circumference at any distance r, and h is the height of aquifer at that point. So 2 pi r h is the area and k del h by del r is the velocity. Now h del h by del r we can combine as pi r k and del by del h square. So the term 2h and del h by del r, they can be combined to form this term. So q becomes pi r k del h square by del r, and as we have seen from here, or here, del h square by del r will be C1 over r. So it will become pi k C1, which we have already derived in terms of any h1 and h2, or if we take the radius of the well and the radius of influence, now as we have seen for the confined aquifer case, measurement of drawdown is much easier. Therefore, we want to express this equation in terms of drawdowns. The only problem here is that this h is a square, and we know that h is capital H minus drawdown S. So when we do h square, because of the presence of the square term, we cannot say that the difference of these two squares is the same as difference of the drawdowns square, because it's not linear. Therefore, sometimes we approximate it and we write it, we can write this equation. In a little bit modified form, and by using some approximation, we can write this term h square minus hw square as h plus hw, h minus hw. Once we separate them out, then this h minus hw term is nothing but the drawdown in the well, SW, which is very easy to measure in the field. And the other term which we have is H plus HW, and sometimes we have to make some approximation. For example, here we can say that H plus HW will be very nearly equal to 2H if SW is small. For small drawdowns, so the logic is that the drawdown typically is very small compared to the thickness of the aquifer H. So if SW is quite small, then we can assume that H plus HW will be almost equal to 2H, and therefore Q can be written as 2k pi H, and H minus HW is SW, K into H is the transmissivity of the aquifer. As we have seen, K into the thickness is the transmissivity, so we can write this as 2 pi TSW. So this gives us an equation which can be used to estimate the transmissivity of the aquifer. This equation is exact, but it cannot be used to estimate the value of K typically, because HW and H values may not be known very exactly. But the drawdown in the well SW can be obtained easily. R and RW also are easy to obtain, and therefore for a known value of T we can find out known value of Q, we can find out transmissivity using this equation. So this is useful for estimating the parameter values. So after looking at the confined and unconfined aquifers, in all cases we have assumed that Darcy's law is valid. Sometimes Darcy's law may not be valid, the flow may not be laminar, where we know that the head loss is proportional to when the flow is turbulent, the head loss is typically proportional to some power of Q. Generally we can take it to be a square, sometimes it is 1.7, 1.8, but we can say that head loss is proportional to Q square. So all the analysis which we have done till now does not account for variation of head loss as Q square. It only says that since we are using Darcy's law, the head loss, or we are saying that Q equal to minus K delta H over L, which says that delta H is proportional to Q. So we will look at some cases where what happens if the flow is not laminar but turbulent, especially near the well. So here the velocity may be small, but as we go near the well, the velocity becomes very large and the flow may not be laminar, it may become turbulent, and then there will be an additional loss because of this proportionality Q square. Similarly, near a well we have a screen and there will be some head loss when the flow passes through the screen. So the total drawdown in the well will be a combination of these three terms: laminar loss, turbulent, and the well screen loss. So we will look at how to combine these to obtain the total well loss, which will define some kind of efficiency of the well.